Hi, in this video we are going to solve a sample exam 2, chapter 3 and 4. The first question they ask you to differentiate the following functions. So we are trying to solve for f prime of each of the following functions. The first one, we have f of x equals square root of x plus 3. Now, in order to differentiate this one to find f prime, I rewrite the square root of x into x to the power of 1/2, because the square roots mean the power of 1/2 and plus 3. And we can use the power rule in this case to find f prime. So to use that f prime, I just bring down the power 1/2 to the front and subtract 1 to that. So 1/2 subtract 1. And the derivative of 3, which is a constant, that becomes 0. So just to simplify that here, 1/2 stays as 1/2, and 1/2 for the power subtract 1, that is minus 1/2. So x to the minus 1/2. And that is the answer for the first problem. The second problem, we are given the exponential function, and if you look at the exponent, it is not a simple exponent, so we must apply a chain rule in this case. We know that if given a function f of x equal e to the x, then f prime of x should be the same thing as e to the x. But now the exponent is not x, but it's something else. Is more complicated. Therefore, I let the whole exponent here to be z. So we let z to be 1/2 x squared plus 2x and plus 1. We let z to be that exponent. We rewrite the function f as what? As e to the z power. And to find the derivative f prime, remember e to the z or e to the x is the same thing for f prime. So f prime is also e to the z power, but we are using the chain rule, therefore we multiply by z prime, because we let z to be that whole expression here. Now given z equal this expression, I can find z prime. Again, using the power rule, bring down number 2 down here. So 2 over 2, subtract 1 from 2, that's become x to the first power. I don't have to write number 1 here. And plus 2x, this is 1, the power of 1. So I bring down the 1 times 2, that's also 2. Subtract 1 from that, which is x to the 0. And the constant, when you take the derivative, should be 0. So that should be 0. And simplify that, this is 1. So x, and x to the 0 is 1, so we have 2 here. So plus 2. Okay, so z prime is x plus 2. We know that we were given the expression that the function in terms of x, so at the end you want to have the x variables, not z. So we simplify that one more step here, e to the z, but z is this whole expression, so we plug that back in here. So 1/2 x squared plus 2x plus 1, and then multiply by z prime. Z prime is, we found here, which is x plus 2. And that is the answer for B. For C, this is the function for x multiplied by ln of x. So for the ln of x, just a quick review. If we are given f of x equal ln of x, the derivative of that f prime of x is what? Is 1 over x. Okay. Now, this is the multiplication between x and ln of x. The product, that means we have to use the product rule from section 3.4. And in this case, I let f to be in the formula that from section 3.4, we let the first function to be f, the second function to be g. Just ignore the f of x for now. Imagine we have two different functions here. So I let f to be x and g to be the second function. Then from the formula, we know that the first function prime multiplied by the second one add to the first function original function multiplied by the second one g prime. Now we know that the function f is, we let that to be x. When we differentiate that, f prime, this is the first power, so bring that 1, subtract 1 from that, that becomes 1. How about g prime? We know that g equal ln of x, so g prime, remember the rule here, which is 1 over x. So we have f prime, we have g prime, all we do is we plug in here. So f prime, which is 1, so we don't have to write anything, and g, which is ln of x, plus f, which is x, g prime, which is 1 over x right here. Now simplify that, we can see we can cancel the x term. Therefore, I have ln of x plus, can I cancel out the x? I have only 1 left. So ln of x plus 1 is the final answer. Okay, the next case. Okay, here is the quotient between two different functions. On the top is x, on the bottom is e4 to the 2x. This is the quotient, so I have to use the quotient rule. So again, I let the top function, the numerator, to be the function f to be x, and I let the bottom one, the bottom function, to be g, to be 4 to the 2x. Okay, so from the quotient rule, when we want to find f prime, or when we want to differentiate this whole expression, just ignore that this is another f, not this one here, because I may use a different notation for this one. It's happened to be that we use the same f for the top here, but this is not the one we mentioned here, because we just want to have the same notation with the formula that you saw from section 3.4. So basically, I just want to differentiate the whole expression here. So according to the formula from section 3.4, it's f prime times g minus g prime times f over g, the whole quantity square. Right, this is not the same thing as this function here, so just ignore that for now. It means that we differentiate this whole expression and to get that formula, and f is the top function, g is the bottom function. Okay, now all we have to do is we have to get the expression for f prime, g prime. We let f to be x, so we can easily find f prime, which is become 1, because this is the first power. However, for the g function, it is a bit more complicated. Remember, if I have the general function f equal a to the x, and I want to find f prime, remember, we get the same thing, the same quantity again, but we multiply by the ln of the base, and that is the general formula for any function with the type a to the x power. Now the same thing to here, the base a is 4, the exponent is 2x. This is not x anymore, this is 2x. Therefore in this case, I have to use the chain rule. I let z to be 2x, and g prime, when I take the derivative of g, I should get the same thing, because now g is 4 to the z power after we let z to be 2x, so g equal 4 to the z power, right? So g prime from here, which is also 4 to the z according to this formula, because we have one variable only on the top, and multiply by the ln of the base, which is ln of number 4. Because we let z to be 2x, that's why we need to multiply by z prime at the end. And z equal 2x, when we take z prime, that's also become 2. That's easy, constant 2. And all we have to do now is simplify this here. 4 to the z, which is 4 to the 2x, we get back everything in terms of x. So g prime, right? ln of 4 stays as ln of 4. Z prime now, which is also 2. So this is the expression for g prime. This is the expression for f prime. No, f prime is 1. So we go back to the formula here. F prime, which is 1, so I don't have to write that, multiply to g, and g is the bottom function right here, which is 4 to the 2x minus g prime. G prime now is this whole expression here. So that is 2 ln of 4 multiplied by 4 to the 2x, and f, it's just x right here, right? F is the top function, so it's just x, and then over g squared, the original function g, which is the bottom function, 4 2x, the whole quantity squared. Okay, now let's just simplify that one more time. On the top, it's look like that I cannot do anything else. For the 2x here, minus I can bring the 2x to in front of here, but we cannot simplify anything. I can put x here, and then times 4 to the power of 2x. Right? We cannot do anything here, and then over 4 to the 2x squared. Actually, we can rewrite the top, I mean the bottom, for 2x squared mean for 2x times 4 2x. And now we can see that the common factor for 2x, for 2x here, for 2x here, so we can cancel that common factor if we divide that the top and the bottom by 4 to the 2x power. Then we should get what? 1, because we divide that by here, we got 1, and then minus 2 ln of 4, and then multiply by x, and then over 4 to the 2x, and that is the final answer. Okay, so that's all we can simplify to the very last step right here. Okay, so don't mess up this f prime is. I mean to differentiate this whole expression, and f is the top function, g is the bottom function. The last problem for part 8. Now we got something look complicated here. E plus 1 over 1 plus 1 over 1 plus e. Now this is the function f of x, right? But we don't see any variable x here. That means this whole thing is just a constant. Remember, e is the natural number. Is equal to 2.71828, and if we plug in 2.71828, this is the natural number. We plot the fraction here. They're just a constant. We don't have any power of x involved, any variable x involved in this case here. Therefore, the whole thing here, it just equals some constant. And if I just want to find the derivative of a constant, that should be 0. Because any constant, there's no rate of change, or the derivative should be 0. F prime of this one, the whole thing should be 0. So just be careful. This is the function of x, so we must look for the variable x in this case, and we don't see anything, so this is not a function of x. This is just a bunch of numbers adding together, dividing e, and e is 2.71828. Okay, so that's the first example. I mean the first problem. 5 points. Each differentiate the A, B, C, D, and E. The second problem. We let the function f of x to be 10 to the 4th power minus 4 to the 5th. Now, part A, find the derivative of f of x. This is easy. This is just using the power rule, right? Because this is all the power function. So to do that, it's easy. F prime of x. This is the power rule. So I bring 4 to 10, bring it down. 10 times 4, 40. Subtract 1 from 4, that's become 3. Minus 5, bring down to 4. 5 times 4, 20. Subtract 1 from that, that's become 4. Now, because we are doing another the other parts here, so it's better to factor out this one because we are solving for the zero function from part B. So it's easy just to factor this out from here too. So if we want to factor out this one, the common factor of these two terms, we see 20 and 40. So I can pull out 20. x3 and x4, I can pull out x3. So the common factor of these two terms is 20x to the cube or 20x to the 3rd power. I pull out 20 from 40. I have 2 left, right? I pull out x cubed. There's no more x left on the first term. The minus side carry it here. 20, I took it out. So there's no more the number, the constant. x3, I took out x3. x4, therefore I have 1x left. So this is the factor form of f prime. And the reason that I want to factor out this one because I'm solving for the critical point here. To find the critical point, I need the factoring. Okay, the critical point is the point or the points that make the f prime function to be 0. So to find the critical points, I just set this expression here, or f prime, to be 0, or when f prime is undefined, and solve for x. In this case, this is just a power function, polynomial. So it should be defined everywhere. There's no restriction. So the only requirement for us to find a critical point is just to find the values that make f prime to be 0. And this is 0. That means I set this expression to be 0. Okay, this is the factor of these two terms. Multiply together to equal to 0, and the only way that make this to be 0 is either x to the 3rd power equal to 0 or 2 minus x to be 0, because there's no way 20 equal to 0. 20 is already 20, and using the 0 factor property we can solve for these two requirements. So x cubed to be 0, take the cube roots on both sides, so x should be 0, and then we move x to the right hand side, so x should be equal to. So 0 and 2 are the two values that make f prime to be 0, or these are the two critical points of this function right here. Now the next part asks you to find any local max, any local min. Okay, so to find the local max, the local min, and after we got the critical points, we can use the first derivative test to solve for that. Okay, so let's try. I got a critical point, so that's easy. I know that I can show the numberized system. I have two critical points. 0 is here, 2 is here, right? So it's look like that I can divide this into 1 area, 2 and 3, and do some testing. Now this is the first derivative test, right? F prime test. Now On the left side 0, let's pick one point, minus 1, f prime of minus 1, and go back to the function of f prime we found here. When I plug in minus 1 to here and here for x, I got some value less than 0. That means the function is decreasing. And then between 0 and 2, let's pick one point, 1, right? F prime of 1. So also go back to this function right here, plug in 1, and if I do that, I get some number bigger than 0, or the function is increasing. And then on one point to the right of 2, let's pick f prime of 3, right, on the right side of 2. And if I do that to here for 3, I should get something less than 0 or decreasing. So you can see decreasing, increasing. So this is the local mean, right? This is the mean, the local mean. And then increasing, decreasing. This is the top, or should be the local max. So x equal 2, x equals 0 give you the local mean, the location to get the local mean. And when x is equal 2, you should get the local max. Okay, the last one, not the last one, for part D, next to the last one. They ask you to find a global max and global min on the interval 1 and 3. Remember, global is different from local. Global is the maximum or the highest value on the entire regions. The local max is only max around that local area, but not on the entire regions. So when we are considering for the interval from 1 to 3, we need to also check the two endpoints and make sure that the highest value is the global max and the lowest value should be the global min. Okay, so let's do that now. Between the interval 1 and 3, from the last part, we got the critical points to be 0 and 2. Those two are the critical point. And only 2 is the one that falls in this interval. So to check for global max and global min, we check for the critical points that are inside this interval and the two endpoints 1 and 3. And it's happened to be that is only 2 is the only critical point that is between 1 and 3. Therefore, we check the value for 2. Make sure you check the original f function, not f prime, because we are looking for the maximum value of the function of the original function. So we check f prime of 2, f prime of 3, which is the right hand point, and also f prime of 1. And using the normal function right here, I plug in 3, I plug in 1 and 2 to here. I got it from here, and check for the value. So we know that if I plug in 1 to here to find the f of 1, we got 10 1 to the 4th power minus 4 to the 1 to the 5th power. This is the original function. Anywhere I see x, I plug in 1, and that is 6. And then do the same thing for f of 2. I got 32, and then minus 1, 62. And we can see that the highest values between these three values is only 32. So this is the global max, and this is the smallest value between these three. So this is the global min. Okay. All right. The last one. Find any inflection points of f of x. So anytime that we are talking about the inflection point is the changing point the switching point between concave up to concave down, or from concave down to concave up. And anytime that we want to find the concave up or concave down of the functions, we must check the second derivative, okay, which is f double prime. We got f prime up here, right here. So I rewrite here f prime to be 40x3 from part A, 20x4, and f double prime. It's easy to find f double prime by using the power rule. Bring down 3 to 40. 3 times 40, that is 120. Subtract 1 from that, x squared, minus 4 to 20, that is 80, and subtract 1 from that, which is 3. And we can also factor this one because we want to find the critical points of the inflection point. Remember, the critical points for the possible inflection points should be the second derivative that make this one to be 0. So that's one. I want to show this one to be 0 and so for x. And the best way to show that is by factoring. So I can pull out 40x squared because this is the common factor. So I pull out 40. I have 3 left because 40 times 3 is 120. I pull out x squared, so there's no more x, minus 40, 80 divided by 40, that give me 2. And then I took out x squared, I have 1x left here. To find the critical point, we set this thing to be 0 to find the critical point, right? So this thing to be 0, meaning that x squared to be 0, or this expression here to be 0. And x squared equals 0 is telling me that x should be 0, and for here this should be 2. I plot 2x to the right hand side, 3 equals 2x, and then I divide both sides by 2. I get x to be 3/2. So x equals 0 and x equals 3/2. These two are the critical point, right? The critical point. The critical point. And to test for the inflection point, again we use the second derivative test here. I have 0, I have 3/2. So we are testing for f double prime. Okay, so I pick one value on the left side of 0, or maybe -1, f double prime of -1. So I plug in -1 to the function of f double prime right here, x and x. I got some values bigger than 0, right? So around this area on the left side of 0, -1, bigger than 0, which is positive. Positive is concave up, right? Positive. And then between 0 and 3/2, I pick one value, maybe 1, f double prime of 1. And I got something also bigger than 0. So this is also positive, concave up. So we don't see any changing yet. So there should not be the inflection point at 0. And how about one point to the right of 3/2, maybe number 2. If I do that, I get something less than 0. If I plug in 2 to f double prime function, then I get something less than 0. And negative for f double prime is concave down, the sad phase. Concave up, the happy phase, positive. So here we can see there's a changing between concave up and concave down as 3/2. So 3/2 should be the inflection point. Okay, that is the long problem number 2. Let's try the next one. 3. A company is selling a product for $30 each, and the manufacturing cost can be modeled by the function C of Q equal the expression. So this is the cost function for producing Q units. Now for each of the quantities below A, B, C, determine whether the company should increase, decrease, or not changing the production levels in order to maximize the profits and justify your answer using calculus. Okay. So the key point here, the key word, is that you want to end up with maximizing the profits. Okay, profits. So profits is the term that we are trying to look for. Now the profits is equal to the revenue subtract the cost, right? That is the profits equation. Remember the profits it should be equal to the revenue subtract the cost function. We got the cost function, but we didn't have the revenue function, so we have to do that now. The revenue function for any Q product is the price times the Q, PQ. The price times the quantity is the revenue. We know that for each product is sold as $30, so the price should be 30 Q. So this is the function for the revenues. And now we can find the profits function. The profits also P of Q equal to R of Q subtract C of Q. R of Q is right here at 30Q. Subtract C of Q is what's given right here, C of Q. That's long expression. So Q 3 minus 9 Q square plus 45 Q plus 15. And if you do the distribution of the minus side to here, to here, to here, and here, and simplify that, you should get minus Q3 plus 9Q squared, combining right term, 15Q, and minus 15. This is P of Q after the simplifications. Now, this is the profits, and the question is asking for maximizing the profits. To maximizing the profits, we are looking for the local max, right? The global max. So all the max value, local max, local min. In this case, maximizing is the local max. And to find a local max, you are finding the critical points and then setting that equal, finding the critical points and do the testing for the first derivative testing. The same thing as the other problem that we saw before. Now, to find the critical points of this profits function, we find out the P prime first, right? P prime, because P prime is the function that we are setting it to 0 to solve for the critical points. Now this is easy. I can print out 3. This is the power rule. Print out 3, subtract 1 from that, and then print out 3. 2 times 9 is 18. Subtract 1 from that, and this is just minus 15. And the constant minus 15, when we take the derivative, it should be 0. And because we are setting this equal to 0 and solve for Q, for a critical point, it's always easy to factor because we are solving for 0. So we can see we can pull out minus 3 as a common factor. I pull out minus 3, I have Q squared, I have minus 6, right? Minus 6Q, because minus 6 times 3 give me plus 18 again. And then minus 15 divided by minus 3, that is plus 5. And we want to further factor out this trinomial. This is the secondary trinomials. 3 terms. The square term has a coefficient of 1, so we can factor out this one into the product of 2 binomial. Q and Q give me Q squared. Now the 2 numbers here, when we have the products, it should be 5. When we add the 2 number here, we should end up with minus 6. and that should be minus 5 and minus 1, because minus 5 times minus 1 give me plus 5, minus 5 minus 1 give me minus 6. This is the factor of this trinomial, and then I bring down minus 3, and we want to find a critical point. So we're setting b prime of q equal to 0, and so for q, this is easy. Using the zero factor property, we can just set these two expressions to be 0, q minus 5 to be 0, or q minus 1 to be 0, and then adding 5 on both sides, q to be 5, the critical point, and then adding 1 to both sides, q to be 1. So the critical point, this is the critical points, 5 and 1. Okay, so 5 and 1, we are looking for local max here. So that plot, okay, this is 0, 1, 2, 3, 4, 5, 6, and 7. The critical point 5, which is right here, and 1 is also here. Right. Let's do some testing. Okay. Now, they ask you, as the quantity of 2 is right here. So let's try to do some testing first, and then we can make the conclusions. For anywhere on the left side of 1 is the critical point. So we pick one value on the left side. So maybe 0 for easy. And then 0, we plug back to here, b prime of 0, because we are doing testing for the first derivative of the profit function. So p prime of 0, which is the left side of the critical point 1. And I guess if I plug in 1 to q for this function right here, I end up with something less than 0, so which is decreasing on the left side 1. Now, one value on the right side 1, let's pick 2. So p prime, the profit 2, and also p prime is this function as well. Plug in 2 to here, q. I got something bigger than 0, so it's increasing. It's increasing, right? And then one value on the right side of 5, because this is the left side of 5. The right side of 5, let's pick 6, b prime of 6, the profits, the p prime of the profits, which is also this function here. So q now is 6, and I got, this is something that is less than 0. So this is also decreasing. Okay, so now after we do the testing for p prime function, we can make the conclusion about a question here. They ask you when to maximize the profits. Should we increase, decrease, or not changing the production levels in order to maximize the profits? And we are doing some testing right here. Right here. So if I have q to be 2, q to be 2, q to be 2, which is right here. Q to be 2 is around here, and q to be 6 is all the way here, and q to be 7 is also all the way on the right side. So we know that this is going down, up. This is the mean value, so we're not looking for mean, we're looking for maximizing the profits. And this is going up, up all the way to here too, so this is also up. Because on the left side, 5 is all the way up. So it's up, 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 and then down. Therefore, the max is right here. This is the max. Therefore, the q equal 5 is the level that makes the profits to be maximized. So this is maximizing the profits. Okay, maximizing the profits. So if we know that Q equal 5 is the point, the level that maximizing the profits, that means Q equal 2, should we increase or we decrease? We know that Q equal 5 is maximizing. So Q equal 2, in order to maximizing the profits, we have to get 2 up to 5 to maximizing the profits. So that means we have to increase the value at this point, because we need to get to 5 in order to maximizing profits. How about Q at 6? Because 5 is the maximizing profits, and if I go all the way to the left here of 5, 6, 7, and 8, I'm going down. So do not do that. You do not want to increase 6 up. We just want to get it down to 5 to maximizing the profits. So therefore, at this level, we should decrease. Same thing to 7. 7 is all the way to here. You don't want that. You want to get back to 5 to maximizing the profits. So it's also decreasing here. So it's only A as a Q of 2 that you want to increase the profits, because at this level 2, if we increase all the way to the right up to 5, we'll make the maximizing the profits. So that's why we increase the level of 2 up to 5 at this level here, increasing. And that is part question 3. Okay, the next question. 4. 4 is the cost of producing Q units of a good is given by the cost. This is a cost again. Now they ask you what are the fixed costs and the marginal cost, the average cost. Okay. The fixed cost is the cost that you have to pay, even though the production level is 0. Right. So let's try to find the fixed cost first. The fixed cost is the cost you have to pay to pay, even if the production level is 0, even if there's no Q. So which is C of 0. That means when Q is 0, no production, what should be the cost? So C of 0. We plug in 0 to here. 0 make this term to be 0, so that's 1,000. So the fixed cost is $1,000 million. So 1,000 millions dollars. The marginal cost. The marginal cost is the cost of producing the next level. So the marginal cost MC of Q, we can find the marginal cost by taking the first derivative of the cost function, or C prime of Q. And finding the derivative function is easy. From this case, I bring down 2 the power rule, 0.1 times 2, that is 0.2, and Q. The derivative of 1,000, which is constant, that becomes 0. So this is million of dollar per unit, because this is the cost of producing the next level of units. And the last question is the average cost. The average cost, AC of Q. The average cost is equal to the total cost C of Q divided by the quantity Q. In this case, the C of Q is 0.1 Q squared plus 1,000 divided by Q. And the units here is million of dollar over Q is the unit. So million of dollar per unit is the cost, the average cost units. Now, as to what production level does the average cost have a critical point? So we remember from the lecture, MC of Q, the marginal cost, equal to the average cost. So when the average cost is equal to the marginal cost, at this point we have the critical point for the average cost. This is the function, the equation. When the marginal cost equal to the average cost, this is the production level that gives you the critical point for the average cost. And to solve for that production level or Q, we are setting the two equations to be equal to each other and solve for Q. MC is the marginal cost, and we got that from here, 0.2x, right? 0.2 Q, sorry. AC is the average cost, we got it here.
Here's what I found on the web.
And we got 0.1 Q square plus 1000 over Q. And I multiply Q on both sides because I want to get rid of the fraction here. So multiply Q on both sides. So multiply Q and Q. I can cancel the Q, and Q become Q square. So 0.2 Q square equal 0.1 square plus 1000. And then I can subtract 0.1 Q on both sides. So I got 0.1 Q square equal 1000. And then dividing 0.1 on both sides, I have Q square equal 10,000. And then take the square root on both sides, I got Q to be 100. So as the production level of 100 units, the average cost has a critical point. Now, the last question they ask you is that critical point that we found here is the local max or the local min or neither. The hint is using the second derivative test, so that's easy. Alright, if we got the critical point, then we can use the second test by plug that in the second derivative and test to see if that is positive or negative. Now we got the AC, the average cost. AC is right here. This is the function for AC. AC equal this one. So let me rewrite AC is here. AC of Q, and if I just divide by Q on the first term to Q, I got 0.1 Q, and then the second term 1000 divided by Q, which is 1000 over Q, and I can bring up the Q to the top, putting the -1. And if I want to find the second derivative, I can find the first one first using the power rule. This is the first power, so we have 0.1 left only, and then -1 go to 1000, which is -1000, and then subtract 1 from here, which is -2, and I take one more derivative here. 0.1 is constant, so that becomes 0. So bring down -2 to here to the 1000, that is 2000, and then Q subtract 1 from here, so Q to -3, or we can bring down the Q back to the bottom and putting the +3. And we know that the critical point is the 100, so I plug in 100 to the second derivative test, 100, and 100 go to Q, it should give me some value bigger than 0. So this whole expression is bigger than 0. Wait, hold on, let me check this one. Yes, 100 is right here, and 2000 divided by 100 to the Q power, it should be something positive. So positive is the plus side. So plus is the happy face for the second test, and that should give you the local min. So it should give you the local min in this case. Okay, so that is the question number 4. Now let's try to move on to the next question. The demands for the yams are given by Q equals something, where Q is the pounds of yams and P is the price of pounds of yams. If the current price of the yams is $2 per pound, how many pounds will be sold? Okay, so we are looking for the number of the pounds, right? And Q is the pound. Q is the pound. So basically we are just looking for Q in this case. And Q is given this quantity expressed in here. So Q is that. And as the price of $2 for the P, so I plug in 2 for P. And that should give me 5,000 minus 40 or 4,960 pounds. That is the number of the pounds. Alright. Now the next question is the demand at $2 elastic or inelastic? And it is more accurate to say people want yams, the yams, and they will buy them no matter what's the price. Or yams are luxury items, and people will stop buying them if the price gets too high. So we are trying to see if this is elastic or inelastic first, and then we can make the conclusion about the statement. Now, to find the elasticity of demand, the formula for the elasticity, E, is equal to the absolute value P over Q multiplied by dQ over dP. Right? Okay. So we got the function Q is right here. Okay, so Q equal 5,000 minus 10p squared. So dP over dQ or dQ over dP right here, this quantity here, is just equal to Q prime because we are taking the derivative of the Q with respect to the price P. Or using the power rule, the constant becomes 0, bring down the 2 here, so minus 20p, and that is the value here. I know that this is the absolute value of P of Q, and that's quantity here we just found here, which is minus 20p. And remember, this is the absolute value, so it's take away the minus sign. So 20p and p give me 20p squared over q, and then I can just take away the absolute value size. And when the price is $2, when p is $2, I can find q we found here for $2, which is that number 4960 from part A. We have P, we have Q, which is here. We can find the elasticity of demand, which is 20p squared at the price of $2, so that is 2 squared, over Q at the price of $2, Q is 4960. And this ends up to be 0.016, and which is less than 0. And less than 0 is inelastic. Inelastic. So if this is inelastic, then people want gems and we buy them no matter what's the price. That means this is the first statement should be correct, right? The first one. Okay, so people will buy the yams and no matter what the price, because this is inelastic. So after we found the elasticity of demand, and we can make the conclusions for that statement. which one, the first one or the second one? In this case, should be the first one. Inelastic means the demand is not changing a lot, even if the price does increase. I mean, they will keep buying the products even if the price is increasing. And that is the last. This is the last problem. Okay, this is the problem from section 4.7. There's the rumor among 400 people according to the logistic growth model. This is the model. T is in hours, and N is the number of people. Now, at the time T is 0, how many people heard the rumor? 0 for time, that means T is 0, so we find N of 0. Anywhere you see 0, plug in 0 to T. So T is right here. 0 times that is 0, and E to the 0, anything to the 0 power is just 1. So that's why we got 400 over 1 plus 399. We got this expression here. I mean, this term here is 1. And this is 400 over 400. So which is 1. So only one person. Only one person heard the rumor at the time of 0. After 2 hours, how many people heard this rumor? So we just plug in N equal 2, right? And N equal 2, go to the place of T. So 400 over 1 plus 399, and E to the 2 times minus 0.4, that is minus 0.8. And if you plug that in the calculator, you should get 2.22. And we are asking for the number of people, so we cannot have a decimal point for people, for person. Therefore, we have to round it down to 2 people. Because 2.22 people are not enough for 3 people, so it should be 2 people that heard the rumor, not 3. And then the last one, when does the rumor spread to the fastest? So if I have the logistic curve, so this is the review for the logistic curve. The logistic curve is a curve that is roving from concave up to concave down, and the point that is switching from concave up to concave down is where the function is roving the fastest rate, or in this case, the rumor should be spreading the fastest rate when it is at this point. And this point is halfway between the maximum value and the starting point. Or we know that according to the formula, the numerator, this is according to the logistic curve, the top number here is the maximum number of the function, or in this case, the maximum number of the people that will receive the rumor, and 400 is right here. So halfway before a 400 should be 200. So this is the fastest rate. So as the level of 200 people that heard the rumor, this is the fastest rate. So we want to find the value of T. I don't know what's the value of T that's make 200 people to receive the news. So all we do is we set the whole function to be 200, because that is the middle value, the midpoint, and then solve for the value of T. So if I let 200 equal to the function 1 plus 399 e to the minus 0.4t. Now we can divide. Okay, we can multiply this. Actually, we can divide 200 on both sides first. So 200 divided by 200 is 1. 400 divided by 200 on the right hand side, that gives me 2 on the top. Right, 399 e to the minus 0.4t, just to simplify the function. And now we multiply this whole expression on both sides. therefore on the left side have 1 plus 399 e to the minus 0.40. If I multiply that on the right hand side, that will take away this expression. I have 2 only. And subtracting 1 on both sides, I should have 1 here. And then I want to solve for t, so we try to dividing 399 on both sides. So 1 over 399. We're trying to solve for t. We take the ln on both sides because this is the base e. So ln 2. ln and e is cancel out. At minus 0.40 equal ln of 1399. And then we're solving for t, dividing by minus 0.4 on both sides. ln 1 over 399 divided by minus 0.40 minus 0.4. We are solving for t, and that should give me around 14.97. Sorry, 14.97 hours. So at this hours, there should be 200 people that heard the rumor, or that is the time the rumor spreads at the fastest rate. Okay, so that is the end of this sample exams. We have 6 problems, and that is all. And thanks for watching.